Good day, everyone. For this video, we are going to have a short na Python implementation of regression using least squares. Okay, so linear regression is one of the simplest predictive model in machine learning. It predicts by deriving a straight line formula based on the data fit on it. But as simple as it is still an effective model, such as use cases like this. So we are going to use dataset that was uploaded in Kaggle, but it's also a repository in R, okay? And it contains on the budget allocated for TV, radio, and newspaper advertisements with the resulting sales. And what you wanted to predict is the sales based on the TV, radio, and newspaper expenditures. So first, we have to import the required packages or libraries. We have the NumPy, the Pandas, the Matplotlib for plotting, the Seaborn. This is mostly for design. And then for preprocessing, we want to split our data set into train and test. So, and then we want to build later on, after building from scratch, we also want to show you how you can implement this using a defined package using sklearn, as well as the validation of the model. Now, first, let us load and explore the data set. So we have a data set na advertising.csv. And we are just loading it using pandas, and we can determine its shape using the dot shape in the method in pandas. And if you want to see the first few rows, we can just type df.head. Oops, PD is not defined. I have not run the code yet. So we must run or execute the cell. And after execution, we can now check. Okay, it is now okay. And then we can also, it is also useful to get the summary of statistics of the data. And this includes the count, the mean, standard deviation, mean, the percentiles, the maximum. And we can do this for each column. Okay, and we simply have to use the dot describe the method of pandas. Okay, and now as mentioned, the first thing that we have to do is that we have to observe the association between the sales as well as with the other advertising medium, and we can use that using the correlation. Okay, and we can simply do that using the dot core method in Python. Okay, and it will give us the correlation. As you can see, we have much higher correlation with TV and sales as compared to correlation between the radio and sales, as well as the newspaper and the sales, which means that the strength of the association between these variables are also stronger. Okay, and we can just simply plot this data using the Seaborn, then plotting the heat map, and passing the df.core data or the correlation data, and it will produce as this visualized results. And we can see that the TV and the sales has a much higher correlation than compared to other variables. Okay, since sales is our target variable, so we wanted to identify the variable which it correlates most with. And we have already seen that TV has the highest correlation with sales. Okay, and we can also pair visualize the relationship using the scatter plots. And we can see indeed that the trend between the TV and sales is more obvious as compared to the more dispersed na data of the radio and the newspaper. Okay, and now backing up the findings using correlation, the relationship between sales and TV is more linear. Okay, and what else? Okay. Let us try now to perform a simple nonlinear regression from scratch. Okay, now the first thing that we have to do is to prepare our data. So we have the X and then the Y. And then since we only deal with one predictor, so we have the DF. That is the data frame that we have created earlier. So as you can see, we have the DF that had 3, and it will show us the data for all of the advertising modes, and there's corresponding sales. So we only wanted to use the TV and the sales. So we have the DF of TV, and then meanwhile the Y is DF of sales. Okay, and let's try to print that one. 3. Then we have here the data. So for example, we have the observation pairs X and Y. So we have the TV budget to 30.1 and the sale 22.1, etc. Okay, next is we have to perform reprocessing. So we will be splitting the data set into training and testing because we'll only use the train set for fitting the model. Okay, and we can do that using sklearn. And sklearn has this method train test split, wherein you simply have to pass X and Y, and then you have to determine the percentage of the split. So in this case, we wanted that only 25% of the data set will belong to the test set. Okay, and we also randomize it. So, and then it will return 4 objects wherein we have the X train, the X test, as well as their associated na labels. Okay, and if we try to print it out, we have the train size has 150, and then the test na size has the 50. Okay, now based on this data set, we wanted to estimate or compute for the coefficients. And as mentioned, in order for us to compute for the beta 1 hat and the beta not hat, we have to, one approach is to use the least squares na approach. Okay, so the beta 1 hat refers to the slope of the line or the weight that is associated with the feature. Meanwhile, the beta naught hat refers to the intercept or the bias. Okay, so we have, as mentioned, we have the line which is y, which is equal to beta 1, beta 0 plus the b1 times x, right? So however, at this point, this beta 0 and beta naught and beta 1 are still unknown, and we want to be able to know this in order for us to estimate the values of the y. Okay, so in order for us to do that, we have to implement this one. First, as you can see, is let us solve for the mean of x and the mean of y. So we will fit on the model, so on the training data pala. So we have the x train mean we will solve for the mean. So NP that mean X train, and we'll also solve for the mean of the predictor. So, okay. So going back, we have this TV and sales. In other words, we want to solve for the mean and solve for the mean of the Y as well. Okay. And then we have the Y train mean, which is maybe computed by NP.mean. Now let's print X train mean and X train Y train mean. Okay, and it gives us this values. Now, on the numerator is we have to solve for the difference between every X na value minus the X na mean. Okay, so we have, let's say the DF, we have the X train, right? This X train, we are going to subtract each of the value with the mean. Okay, so we have the X train mean, and this is the result. So let us just store that into diff X. Okay. Now we want to solve for the difference of the each na response minus the mean. So we have the diff Y is equal to Y train minus Y train na mean. We have the diff Y. Okay, and it also gives us a vector. So essentially what we have is the Y train, and each of this will be subtracted by the mean of Y. Okay, which is computed in using this equation. Okay, now next is we have the numerator and this value. So we must multiply these two. So what we have to do next is we have diff X times the diff Y. Okay, and it gives us the value. And in order for us to complete the numerator, we have to take the sum of all this. So we have the NP, that's sum. Okay. And it gives us this value. Okay. Now we must divide it with the squared of the difference of the X minus the mean. Okay. So essentially what we have now is we have the beta 1, and then we have this numerator, right, divided by this diff X, wherein we have to square all of it. So NP, that's square. And then we take the sum of all those values as well. And we have the beta 1. Okay, and we have this value for beta 1. So if you want to visualize this denominator, what we have is like, we have first take the difference, right? And then we square it. Okay, so this is the result of the square. So, and we must take the sum of all this. And that gives us the value. And that will serve as the denominator for the beta, for computing the beta 1. Meanwhile, the beta hat 0, beta not hat, I mean, may be computed using this equation. We have the Y mean, meaning we need this Y train mean minus the beta 1 hat, which is the one we just computed, times the mean of x. So that is the beta 1 times the mean of x. This is the mean of x. So we have the, and store it to beta 0. Okay. And printing beta 0. So now we have the value for the model na parameters using the, that is estimated using the data itself. Okay. Now we have to predict the y values using the estimated na coefficients. Okay. And we simply have to plug in the values of the model parameters here. And TV, meanwhile, is the budget for the TV in advertising mode. Okay, so in other words, what we need is the, say, the y hat. Okay, and we have the beta not 0, so that is the beta 0, estimated beta 0, plus beta 1 times the budget for TV. So in this case, we have the, we will test it on X test now. So we have the y hat, and this now gives you the predictions. Okay, so we have, it gives you the prediction for each na y. Okay, and now we have to evaluate the model using our loss function, MSE. So in order for us to do that, we have to take the compute for the error, in which case it's just the differences between the actual and the predicted. Okay, so we have the y test minus the y hat. Okay, and that this is the difference between the predictions, and then we take the square. Okay, and we take the sum. And that in which case this is the sum. And this actually is the residual sum of squares. And we will store that in our RSS variable. And in order for us to compute for the MSE, we simply have to divide RSS with, or we take the average of this by dividing it by the number of observation or samples. In this case, we have 200 markets, right? Or 200 na. But for just the test set or the Y test, we must determine how many observations belong in the Y test. Okay, and the MSE is 9.17. Okay, and we can also evaluate it on the train set. Okay, we simply have to copy this. This is the train the model. And instead of X test, we will plug it in into the Y train. Okay, and then we have the Y hat. And then we will also compute for the RSS MSE. And then this should be the Y train. Y hat. So. And oops. Where did I go wrong? Okay, this should be X train. And we can also evaluate on the train set. So we simply have to copy this equation. And then instead of X test, we plug it in with X train. Okay, and then we have the Y hat, and we take the residual as well as the cost na function. And that gives us 10.96. As we can see, there is a little to no difference between the MSE for the test set and the train set, and even the test set is even better. No, the unseen na data, our results are even way better as compared to the train's test train results, which means that the results are good enough. Okay, or we did not experience any overfitting. Okay, now